In the next video, I will be doing stuff with some magnets and some ball bearings and the laser level and the webcam, except these will be configured in a different way. I'm going to attempt to make a ball bar. How you guys doing? So in a previous video I talked about producing a ball bar that I was going to do for the CNC machine, and it's been about 2 weeks and I have something that's working now. There was quite a bit of stuff. There was like a lot of hardware back and forth, and then the software and stuff. It's kind of equal between those things. And yeah, so what I've created is this thing here. Let me see if I can get on camera. So there it is. It's using the laser level webcam technique that I was doing before. And this one now also, for joints, I'm using a compliant flexure. So we can see that there. And for the joint here, this is I came up with this. This is I'll call this like a bell joint. So this allows me to dial in the runout and basically get rid of all the runout. So let me turn the camera around and we'll have a better look at this thing. So here's up close of what the ball bar looks like. And it is comprised of 3 joints. So we have the base here, and then we have the main flexure compliant mechanism here. And then we have this joint here. This one here attaches to the collet. And I'll quickly run down through each part and see them up close. So starting over here with the collet joint. So with this, we basically have to put this shaft into the collet, and we have to have this ball here. And this ball, we have to have also 0 runout with this. So that's why I have made a bell around it and with 3 screws. So what I can do is I can dial that all in and get all the runout of the whole assembly. So whether or not the runout is on the spindle, or if it's in the collets, or the 3D printed mechanism and all that, or it could be on the ground washer there. So with all of those, we get to, on the machine while it's running, we can zero out all the runout on that. So on the other side, we have the base here, and it is all held onto this bigger piece of steel. See if I can get this out carefully. So that's all it looks like, nothing too fancy. We just have a series of Neodymium Magnets down there, I think maybe 6 of them, 10 millimeters in diameter by I think like 2 millimeters. And the 16 millimeter ball goes on top of it, and same thing, we got the washer in there, and that washer has been lapped. So all of these joints, I use a sacrificial 16 millimeter ball to lap it in. So I have a series of grits, so starting at 220 and working up to a few thousand, I can lap that joint in so there's like no motion on any sides, and has a really good fit. And increasing the fit I also find helps really well with the magnetic attraction of it, because there's more surface area. So more of the flux magic can happen. So the reason why I have magnets on the bottom of it and not just screw it down or anything like that is what I want to do is attach the collet joint and like forego the compliant mechanism in the middle. And what we can do is we can attach the collet here, and with the CNC machine we can go over and we can find where we want to put the sander, the G54, and we can place it down like so. And with the CNC machine we can apply force. So we can, with this collet joint, we can apply force onto that and hold it into place, and that way it's not going to go anywhere. And once it's on there really good, you can then go ahead and stick all these magnets in there. And with all those magnets, I find when they're doubled up like this, yeah, they kind of fly around everywhere. But that really locks it to that piece of steel, and that's not going to go anywhere. So like I can move it with a lot of force, but like it's on there really good. And this is I think this is 1/2 inch steel. It must weigh about 10 pounds or so. So that's enough to hold it in place and have it so it's not going to go anywhere. And the main attraction is the compliant mechanism itself. So this is Now, as we can see, we have the webcam sensor in there, and then on this side we have the laser, and we have this compliant 3D printed mechanism that works in one axis. And yeah, so we don't have any kind of loose fitting. It's this motion is very nice, feels really good. And we can see if I can move it like that. You can see how like easily it moves. We can see how easily it moves like that. So far this is working pretty good, but there is room for improvement. I'm going to look at having the flexures mirrored on both sides. So with this setup, I have the flexures on the one side. It's actually probably easier to see it from this side. And so what I think I'll probably do is add it so it's symmetrical, because even though it's quite stiff in this orientation, it is kind of weak. If I squeeze this way, I can buckle and collapse the flexures. And if I'm constantly in any direction pulling on a flexure instead of compressing it, I think it'll hold up a lot better. So there were a few iterations on this whole setup. From the flexure, starting with that, I was trying this setup here where it's like there's like a flexure in the center of it, and that was the intent of that was to produce stiffness and like an additive stiffness. So like as I move this back and forth, there's going to be resistance like that, but with another flexure that is applying a positive force along that axis, it's possible to make it so the flexure has zero stiffness. And you can see on YouTube videos how that works. I didn't have any success with that. I think you really have to simulate this stuff to really get it correctly. You can't really just wing it like I'm trying to do. After that, I was trying to increase the flexures, same keeping with this zero stiffness thing here. I was trying to make it work a lot easier with multiple flexures on this side, sort of like zigzagging back and forth. And ultimately that did not work at all. So we can see how easy it is to move, and like it's not really constrained in the two axes that I want it to. It just kind of moves everywhere. It can also rotate. So after that, I went back to one of these designs here, and I cut out the center flexure in the middle, and noticed it was a lot more light. So this one here is practically what I've been using now. The difference was with this one, it was a 2-part 3D print. So we can see on this side here where this lever comes out, it bolts into the inner flexure piece because I wanted to have a rigid connection on this side. And ultimately what I ended up doing, if I go back to the original one here, this one now, like the lever is, it's full depth on both sides, and there's a hole cut out there. But I can get away with that because I have this part here that holds a laser in place, and I use that as a supporting structure to hold the whole thing together. There is a lot of room for improvement on this setup, so I do intend to make a different version, a new version of this one. Starting off the laser, I'm going to replace it with these smaller red lasers. And I believe these ones, they also have current limiting resistors in them as well. So they're much smaller. They're 650 nanometers, well they should be, and I think they're 30 milliwatts. So they should be at the power characteristics that I want on a laser that's shining directly onto a webcam sensor. And the webcam sensor itself, there's a few problems with this. So number one, the resolution, it is 1080p, but it's only 30 frames a second, and that's not really that great for capturing real-time motion. So I'm going to look at one that is 720 that can shoot at 120 frames a second. And second thing is I don't know what kind of sensor is in this, so I don't know the size of the pixels. So that is a problem because I don't know the scaling factor. I need to figure out the micron size. And what else? This board runs off of USB, and USB, just due to bandwidth on this board, they do compress it to mjpeg, which kind of is a problem just due to artifacting of the JPEGs. So I will be looking at running it on a Raspberry Pi Zero, a new board that I can run through the camera bus on that, and that should be able to give me a raw feed, and possibly I could even do the processing side of the sensor part on the Raspberry Pi Zero and then transfer it wirelessly. So I'm going to look at that, and I also have some filters that only accept 650 nanometer, so this red laser, and I'm going to put that over top of the new webcam or the new camera sensor, and hopefully that will filter out all the fluorescent lights and LED lights, sunlight, everything else. So I'll have like a much cleaner feed of data. For powering the laser, I am using this boost buck converter, and it's got a little LED screen on it. And this is working all right. This laser on its own, it needs to run on 12 volts, and I'm not sure what the current pole of that is. But I'm running this thing really, really low. I think I'm running around 5 volts or so. It's barely enough to keep the thing functioning, but it reduces the intensity of the laser beam onto the sensor by quite a lot, and I need that because I want the gradients of the blurriness of the laser on the sensor, because that helps with centering the Gaussian distribution. And without it, if I'm just getting like pure white pixels, it's just not as accurate that way. So it is kind of necessary, and that's where the new laser emitters, diodes, will come into play. So if we look at the collet joint, you can see how that looks, and let me just put a ball in place there. And I think it's still calibrated. It has a few extra features. So I have like an outer bell and then the inner shaft on the inside where the Neodymium Magnets are, and the shaft that goes into the collet. And there's a bit of a gap in between them, and that's for allowing this whole setup to be trammed in so I can get at the runout. So with this setup, I can get the runout from the ball down to, with these current like coarse threads, I can get it down to about 5 microns. And I know that because when the ball bar is all set up, I'm getting live feedback of its length. So what I can do is, as I'm looking at it on the display, I can spin this and I can go ahead and adjust them, tighten and loosen them until I get the ball completely zeroed out. So a quick disclaimer, I'm going to go through the running operation of this particular ball bar. And this is not representative of all ball bars, nor am I a CNC machinist. I'm really just figuring out this stuff as I go. So I'm going to give my interpretation of all this. If you're looking at getting something, a ball bar for a large scale machine shop, obviously you're going to be using some of the professional versions and not trying the DIY solutions such as this. The main thing with a ball bar that you'll come to realize is you're able to track all kinds of problems with a CNC machine with just one linear value coming in. And you can get that because when you have the base stationary here and you're tracking any distance between the base and the spindle, you're tracking the combined artifacts from the entire CNC machine to get to there. So with that one value and tracking it over time, and also keeping track of the time and how fast things are moving and stuff, and moving in both directions, you can find out so much from the ball screws to servos and deformation, if there's any deformation in the machine, how square it is. You can find out all kinds of stuff by just looking at the data and the results for that. So I got the CNC machine on right now, and I'll go through the process of calibrating this whole setup so we can see what's involved in getting this thing correctly aligned. So first thing I got to do is take the ball bar off. Otherwise I'm going to destroy it, and I don't want to do that. And what we're going to do is we're going to move the spindle back to the origin, which is over here, because we need to figure out where this origin is. And I had the CNC machine turned off, and I'm not going to center it out again, so it's going to be off by a little bit regardless. So my machine running, I'll send a G0 to X and Y. So we'll go G0, X0, Y0. So that's going to give us the origin again. So what we'll do is, well, I have all the magnets on here. Let me just flip these off quickly. And we need a ball placed And just to make sure there's no crap on it, just kind of work it a bit and get the magnets out of the way. And now I can press it into the ground there. I'm going to slow it down so it's a little bit slower there. So with a little bit of pushing, and there's a bit of preload on it now, so it's not moving anywhere because the whole spindle is pushing down on it. I can go ahead and drop these magnets in, and that's going to keep it all in place. Oh no! So now I'm going to move it over to where I have it programmed to be, like what the distance is after I found it. So I will jump into the other tool. So I know from previous testing with this that the ball bar radius is 267.839 millimeters. And I'm going to run and move that to that position now, which is out there. And now I can put the ball bar in place. So I drop that one in there, and then that one's going to snap in there. So this is LinuxCNC. If you haven't seen it, this is Qt Dragon. There's many UIs for LinuxCNC. I'm going to launch the tool, the awesome ball bar tool, and here's what that looks like. So this tool is very similar to the laser level webcam tool. Many of the widgets and stuff, such as the feed from the camera feed, and the analyzer, and some of the functionality to all that stuff has been ripped out of that tool into this tool. The only real new thing is the polar graph and how I'm hard coding the 0 position of this. So that red line there, that's 0, and then the green line is what the sensor and the analyzer are determining. So what I'll do is make this smaller, and I'm going to bring up LinuxCNC again, and then the tool, and I'm going to pin this to be always on top, just so I can operate LinuxCNC at the same time in manual mode and the slowest value. So let me just move this up a bit. So right now I'm going to drop this down to 30 millimeters a minute. So when I move this back and forth on the analyzer tool, I'm bringing up position of the final value. So on the left side, you can see that the camera feed of the laser looks all funky like that because I have the voltage cranked down a lot on this boost buck converter. So it's chopping it and it's not producing a nice smooth voltage. Plus I'm heavily undervolting this laser. It's probably a combined matter of that stuff. This is kind of more of a high powered laser, but I'm using it I'm trying to drive it at 5% of its power. But all those artifacts, that's not really too much of an issue because with this tool you're kind of taking this Gaussian distribution and trying to find the maximum point of that distribution. Smoothing does help. So you'll see here that that's what the smoothing does. On this tool, a little bit of a value, it helps just to get rid of some of the very high frequency noises. So if I bring it up a lot, we'll see that the value starts to smooth out a little bit. But I find less is more, so I like to just go something like that. What we need to do is we need to move this up to be 0. It's really, really difficult with 30 millimeters a minute. Yeah, that's actually pretty close there. So I'm going to keep it at that. One thing I found with this whole setup is thermal expansion still is a problem. Currently I'm in the garage. It is nighttime and the garage is getting warm because I'm in it and the CNC machine is running. I do find that this whole setup, even though the ball bar and all that stuff is combined and to be a very close unit, it is not very susceptible to vibration, external vibration. If you're walking around, stomping on the ground, or even tapping beside it, it affects both the laser and the sensor equally, so you don't really have much vibration issues. But thermal expansion of this whole CNC machine, as it warms up and changes degrees, that's still a problem. I find this thing can be fluctuating 30 microns. So we'll run the tool now, and we'll hit start, and it's going to ask us to install the ball bar, and it's also moved out. If you look at the value, it's 1000 and it's 1100 microns, so the scale is off by a little bit. it should be 1000 plus microns. And what I've done is I've moved out by 1 millimeter. You'll see that later when I'm validating the results. I use a feed in and a feed out to determine when I'm stopping the motion and when I'm starting the motion, because I'm going to run the tool first counterclockwise and then I'm going to run it clockwise. So with installed, we'll hit continue. And we'll see now that it's just running. So it's recording the data. Yeah, so it's going to make a complete loop, and I got to fix these wires because it's going to... So one of the issues I'm having so far with the ball bar is you'll notice that the joint there, so it's on a ball, and it is not constrained whatsoever to move in any of the rotations. Also twist, and twist becomes an issue. So currently the design with twist, it's as I'm twisting it, it'll show like a distance change. So what I need to do is I need to constrain the twist. So I have ideas with that, how to do that. So that'll be in a future version. So it's making its way around. So it's going to stop and then it's going to pull out and pause, and it's going to go back in. There it is. It's going now in the opposite direction. So normally in this case, it's doing a pretty good job keeping the laser upright and keeping it from twisting. So I'll have to be looking at that. So this test should be pretty accurate to the CNC machine. And what I found is, and we'll see this in the data, that motion in the forward and reverse direction, you'd think that they would overlap pretty good. But in the case of my machine, they're off by quite a lot. So it's going to be finishing up now. And there's the data. So here's what the data looks like after running that. And it looks better than before my other previous tests. You can jump over to VS Code, and so I printed out the samples. So it did a total of 2,700 samples, and that per degree is wrong because I was calculating that by total. So it's actually half that because it went in both directions. We can see down at the bottom after it runs the filtering how many samples it did in both directions. So it's not always the same. Sometimes they're pretty close. Like this time it's actually quite close, and other times it's all over the place. I'm still working on the filtering part of this. You'll notice that there's a value around right over here. Looks like probably around 450 or so. In the filtering portion here, I have it up already. So what this is doing is it's taking the list of samples and it's looking for, it does a whole bunch of things for filtering. First it does it by separating them into two chunks by threshold. And then after that, it identifies contiguous segments. And what it does with that is the two groups of samples, they're kind of like rough cuts. But on both sides, it's like kind of roughly at over 1,000 microns, just because I'm starting at that point. So it's trying to determine what are actual good data and what is kind of like junk data. And it tries to throw it at it. So I'm still working on that portion, but it looks like it's pretty close regardless. Like if we just kind of omit that spike there, that's kind of what it would give us. It looks like on this test we are able to see on the counterclockwise, it looks like there's possibly a bit of backlash. You can see that on the 0 and 180 degrees. Looks like see how it kind of dips in. This is running in both directions, so you'd think that the values would be all lined up on each other because it moved in the same speed. It's just going reverse, but they're totally off. I'm still trying to make sense of a lot of that stuff. Some things that I figured, you see all the little ripples. So I'm running C5 ball screws. They are rolled. So there's going to be some deformation from what I understand with those types of ball screws. They're not machine ball screws. So I think that's each one of those little shark teeth represents a full rotation of the ball screw. And that's what we're seeing there. I know that the alignment, or the squareness of the machine, I know that that is wrong, because I haven't done it yet. after doing the rebuild, so I haven't gone through and actually squared the whole machine. The non-circular shape, that could possibly be due to that, at least mostly on the red clockwise. We can see how it's kind of like pinched in. It's not so apparent on the blue one, but yeah. Yeah, so that's where I am with things. There's still a whole lot of work to do with this machine. So that's where I am with things. Still have a lot of work to do. A lot of work on the hardware side and the software side. There's definitely some improvement to the software side in terms of determining and splicing out forward and reverse direction. I am running it directly on the CNC machine, so there is, like, I could potentially be talking through Python to LinuxCNC and like knowing when it stops a move and all that kind of stuff, but I've been kind of on purpose not doing any of that stuff because not everybody is running LinuxCNC. A lot of people are running, like if you're doing DIY, like you're using like anything, and then like in the, you know, in the professional world, if you're trying to attempt something like this on a Haas or a Tormac, then you got to be working with their proprietary stuff. So I have this thing set up, so all you really need to do is run G-code and just make it run in a circle, and you can parameterize that circle however you want to do. And then on the software side, all you have to do is have a section at the beginning where it comes out by 1 millimeter and so on and so forth. And then like that like feed in and feed out of a millimeter, like to and from, is kind of how you separate forward and reverse and other kinds of things. And that seems to be working so far so good. Yeah, but on the hardware side, the Flexure, let me get this thing up a little closer. So it works pretty good, but I know there can be some improvements with it. Right now, it's very light in the direction that it's supposed to be. It moves quite well. If I apply force down like this and bend it that way, it is pretty stiff. If I put on its side and put force down this way, it is a little bit more flexy because I can collapse the Flexure in there. So it's just a very simple one. You can see it. This is all 3D printed, obviously. That is 1 layer line thick, so it's not 2, it's just only 1. And yeah, that's quite easy to collapse. What I've had suggestions is to look at a Flexure where it is on both sides, so it's deforming equally on both sides. And I'm going to look at that. But with all this Flexure stuff, I've iterated. I think this is the 4th version of this Flexure. You really got to simulate this stuff. So I need to set up a workflow for simulating. Like as I design a Flexure, I can simulate it and I can see what it does. Because like 3D printing it, that's fun, and you know it's interesting to iterate that way, but it's time consuming. So far, I found that like it's really hard to have a gut feeling of, especially when Flexures get complicated. It's like how do you know it's actually going to work in that direction, to be stiff in that direction, and so on. So that's where I am with things. And also like on the software side, I haven't done nothing in terms of how to extrapolate the data in terms of like determining squareness and all these kind of values. I know like on the Renshaw, you know, there are other ones that are like $30,000, you know, they have that stuff figured out, but I've only scratched the surface so far. I've just got this thing like as a proof of concept, just kind of working right now. So I'm going to continue working on the software. I still have to make a smaller version of this so I can test it in different planes. Currently, I'm only running it in X and Y plane just because it's so large. But I would like to run this thing in like the X and Z and the Y and Z plane and check out like the Z screw as well to see what that one's like. Yeah, so that's where I am with things. Let me know what you guys think. I'm totally not a professional with this stuff. I've just built one. Any comments and helpful points on things, and if you think I'm doing something wrong, I should try something differently, I'd love to hear in the comments. I have all the code currently on GitHub, and I don't have the files, the 3D printed files yet for this post anywhere, but I'm going to get those up there somewhere as well, and I'll link those in probably the description and also on the GitHub repo as well. So I have a few progress videos that I'll show now that I thought were interesting, and it just kind of goes through the evolution of this whole thing, where it kind of started, and you'll see like how the design kind of slightly changed over time just to solve little issues that showed up here and there, and yeah, see where it and how it came to the way it is right now. Okay, so this is the latest one, and I learned some stuff with this that probably could have done through simulating it, but 3D printing this stuff's more fun. So this one is lighter, but I lose the constraint in this axis, and you can see it flopping around there, which is no good. So that's no good. And then like this side. Yeah, so then I went back to the original one. So this is what this one has 2 walls. And I cut out the thing in the middle to see how it behaved. And it was a lot lighter. So I went and did the same to this one, and now this one is extremely light. So you can see if I just touch it, like there's nothing, there's no resistance now. So yeah, this one's perfect. So I'm gonna stick with this. I might just print another one just to get rid of like all these features and stuff that I don't need, because this behaves really well. It's very rigid in this direction. So if I try and bend this, like twisting it, it's very rigid on all axes except this one where it's extremely light. You can just see it oscillating like that. So I got the hardware working. That's what it looks like. I'm noticing now that what I will have to do is flip this around like that, and then what I can do is I can zip tie the wires to the base. Let me just do that right now. So I got this thing running, and I have the base attached down so it doesn't move around on me. And here is what the data looks like. I have to crop out the beginning. The beginning, those blips are when I'm feeding in. Well, there's where I'm feeding out at the end, and then feeding in right there. So that's for being able to determine in the data when this thing starts and when it ends. And the runout, which this will have, looks like this. So I do have a plan for that. Okay, here's the new collet joint. Goes in there, and here's the old one, just a shaft. This one has some screw adjusts so I can sort of align it. And what I did for the washer, I don't know if you'll be able to see this on camera, I used some this stuff here, silicon carbide, 120 to 220 grit, and then I followed up with some of this stuff here, pre-polish. This is like rock tumblers and stuff, but aluminum oxide, this is probably 1 to 2000 grit. So did them after another, and used a sacrificial bearing, all scratched up now. So that does a good fit now. It fits nice, and there's no motion and movement and stuff. So I think that'll work. The screws, the alignment of this thing, because of the washer, like it's not a precision machine thing, it's no good. So some other things on this one that are hard to see. So the shaft on this one here, maybe I'll show the CAD on this. I have 3 relief cuts in there, and then that allows the slicer to put the seam, every layer is going to have a seam, put the seam into one of those relief cuts so it's not actually on the ID of this tube, and then when you put the shaft in, it would be nice and concentric. So this is the 4th version. I ran out of the black material, and it's works. So here's, mind you, the micron values dependent on the sensor with which I gotta measure it again. So I gotta measure it with some gauge blocks, just because I'm not sure what the actual sensor is. But yeah, download it in, it works. It's probably imperceptible from this view. The hardest part is when you 3D print these holes and screw them in, the screws stick a bunch. So I've used some lithium grease on the screws to help with that. I think if I tapped them, the integrity of the screws, the threads would go down and probably strip out on me. So I got to redesign the base. What I'm going to do is base here, I'm going to keep the same. I might reduce the height of it, but I'm going to put a series of pockets around it, maybe 6 of them, and that way I can drop these magnets in. So what I can do is, when it's attached like this, I can move it over to this piece of 1/2 inch, I think, steel, use a spindle, press it down in there so I know it's like where it needs to be, and then I can drop these magnets in and into those pockets, and then they'll hold the base in place, and then like that's not going to move anywhere. So that's where I am with things. It's getting really hot in the garage, so I'm going to stop here and look out for the next one. And yeah, I'll continue with this for a while and see what can come out of this. I will talk to you guys later.